Alrighty, welcome back to this live stream. Today is our last live stream of the semester, sadness. We are going to be talking about quantum physics, which is kind of the last chapter that we have to dive into. And quantum physics is, well, in theory, if you want to learn quantum physics, you would probably have to take a 2-semester course if you really wanted to get the fundamentals and then pretend that you understand it. So obviously there's a lot in quantum physics. We don't have time to do all of it, not even close. And we cherry pick a few important topics that we feel like you should know about so that you have some kind of general knowledge of what's going on in the world of quantum, to a degree anyway. And in that sense, the quantum chapter is very much compartmentalized. There are specific things we want to talk about, and they don't really overlap that much or at all. So for instance, the photoelectric effect is one of them. Bohr's model is another. There's the particle in a box, or the infinite potential well, or however you want to call it, with Schrödinger's equation. That's another category. And there's a few of these, maybe 3, 4, 5 total, no more than that we cover and we expect you to know about to an extent. But again, there's no real overlap. It's very compartmentalized and separate. So what we're going to do today is we're going to do 3 different problems. We're going to do a photoelectric problem because that's a classic. It's quite common to have the photoelectric effect on an exam. We'll do the particle in a box from the point of view of, let's say, a more conceptual angle that's less math intensive, and then we'll do one that's more math intensive because, that might happen. So most of quantum conceptually is complicated, but mathematically is not. The exception is particle in a box. And if you have Bordel, she does like, her 2 favorites are photoelectric effect and particle in a box. Occasionally Bohr's model, but for the most part those are the 2. If you have Speleo, who knows, but he does like Bohr's model. Usually he'll find an alternate version of Bohr's model, which is, it's the same derivation with a different assumption. And as far as particle in a box goes, he hasn't done it that much, but the bad news is that he's done stuff that's way beyond the scope of this class in the first place. So there are occasionally old exams on which the level of math is absurd, and you have to then make a conscious choice in terms of strategy, whether you sit down and you try to bang out whatever you can just by following the math, and might be worth it because most are not going to do that problem, so you can score points where others don't. At the same time, you don't want to spend too much time on that because you'd like to be able to solve the other problems too. So that stuff, you really have to go dive into the old exams. I'm not going to cover that just because I'm not even sure where I would begin covering it. These are problems that belong in an upper div quantum physics class. They're not the topic of Physics 8b. And at that point, you just have to, it really is just math. So there is nothing I could teach you conceptually that will help you solve these things, other than if you do the old problems and you kind of are willing to write down the definitions and then compute the integrals. Most of the time it's integrals. Based on the antiderivatives you're given, then you can do that. But we're going to focus on photoelectric effect and particle in a box. Particle in a box, we'll do one conceptual one, or one on the conceptual side, and one that's more math heavy, so that you have a foundation, because what happens is there is only one particle in a box problem, right? You can't, it is what it is. So how many variations can you add to this problem? Not that many. So you can take it as a baseline and build on it and tweak it a bit to create another problem, and that has been done before. But at the end of the day, it's still a particle in a box problem. So my goal is to teach you the fundamentals that you need to know, so that if you have to replicate them on a slightly different problem, you're able to do that. So let's start with the photoelectric effect. Now, the photoelectric effect is one of these massively important experiments that kind of changed the world of physics, because nothing about the physics that we had before doing this experiment could explain what we observed during this experiment. Now, that is when you know you need to discover something new. Okay, physics works fine until you come across an experiment where what you have does not work anymore, can't predict what's going to go on. So that was the case for induction before that, and then quantum came along at a time where people thought that we had discovered everything we could need to discover in physics, and it was a dying field and you shouldn't major in physics because everything's been figured out. And then we stumbled upon quantum and we're like, oh, just kidding. There's a whole bunch of stuff we not only don't know, but certainly don't understand going on in the quantum world. So maybe don't ditch physics quite this second. And so the photoelectric effect is often used as one of those examples. Now, what it is simply you shine light on a metal and you notice that electrons are ejected. Now, the thing about this experiment is you have to understand globally how it works, because you're going to get some version of this drawing that I made a simplified drawing here, but you're going to get some version of it. It's nice to say, oh, I shine light on the metal and under the right conditions, electrons are ejected, but guess what? I can't see electrons, so how do I know that electrons are being ejected? Okay. Now, electrons will be ejected under the right conditions, which we'll talk about in a second. And how I know that there's going to be electrons ejected is that I need a plate up here that is going to receive or collect the electrons, often called the collector plate. And if electrons hit that plate, then I get a current in that plate, and I can measure the current. And then I'll say, oh, well, you see, that's the electrons are doing that. So there's this plate above the metal, and part of the reason that it's there is to figure out typically the work function of the metal, or at least to figure out how fast the fastest electrons are being ejected. So the way it works is that, yes, you want to measure a current so that you know that electrons are being ejected, but once you've done that, then you make the plate more and more negative, right? You connect it to a device that makes it negative, and if you make it negative enough, these electrons that are going to be ejected, the fastest ones anyway, with the kinetic energy K max, are going to come to a stop right before they hit the plate. So what you do is you start the experiment and you have electrons hitting the plate, so you measure a current, you make the plate more negative. Well, current decreases a bit. And then you make the plate more negative and current decreases a bit, because the plate is now going to repel electrons. Now at some point you're going to reach a level of negative potential for the plate, which is called the stopping potential, that even the fastest electrons that were ejected with kinetic energy K max stop right before they hit the plate, and then they turn around. And the reason why that's interesting to you is because for that particular stopping potential, you know then what K max is, because you can apply conservation of energy. So I say that because it's not just about this, which is often what we talk about. You have to have that plate above your metal so that you can actually perform the experiments and know whether or not electrons are being ejected. Now, when it comes to ejecting electrons, what was surprising about the experiment is that you would think, shining light on it, if you don't get any electrons that are ejected, well, shine more light, increase the brightness. Brightness is more energy. More energy is going to eventually force the electron to be ejected. And it turns out the brightness had nothing to do with electrons being ejected. What was going to dictate whether or not they get ejected is the frequency of the light, or the color of the light, if you want to think of it that way. But the frequency of the light dictates everything, and we had no explanation for that. So you will get electrons that are going to be ejected immediately if you have light with the right frequency, even if the light is very dim. On the other hand, you can have a very bright light with the wrong frequency. Photoelectrons will not be ejected. It's just not going to happen. So with all of that said, which is that was a lot, but I think that was necessary just for context, we have here an unmarked piece of metal in the lab, and to identify it, we want to perform a photoelectric effect experiment because we figure maybe we can figure out the work function and that'll tell us which metal it is. So we have light with an adjustable frequency, and we have this metal plate above that has a negative electric potential for the reasons we talked about before. And you are wearing magic glasses that you found in the lab, and you notice that electrons just barely leave the metal plate when the frequency of the lamp is set to this frequency F0. And then the question is, what is the work function phi of the metal? Okay, so in order to eject photoelectrons in the first place, you need to pay what's called the work function. The work function is the energy required to free this electron from the metal. It's a certain amount of energy. And we know that for the photoelectric effect, the kinetic energy of the fastest ejected photoelectrons, K max, is going to be equal to the energy of the incoming photon minus the work function. So it's a one-to-one interaction, at least as far as we're concerned. I'm not going to get into the nitty-gritty. As far as we're concerned, one photon interacts with one electron. If it has an energy that is greater than what it costs to separate the electron from the metal, for the electron to come unbound, then the difference in energy, E photon minus phi, will give you the max kinetic energy. In other words, the excess energy entirely turns into kinetic energy. Not true for every electron, but the fastest electrons are going to satisfy this. So we are going to get K max is E photon minus phi. Now, what is E photon? E photon is H times F by definition. It is an energy that is only a function of the frequency, and that's what explains the phenomenon, which is entirely based on frequency. For the right frequency, even if the light is dim, you will get electrons that are ejected. Now, we're told in this question that for a specific frequency, F0, the electrons barely leave the plate. Right? They separate from the plate, they come unbound, but they don't have any kinetic energy. So for that specific frequency, K max is going to be 0, which means that my work function, phi, is going to be equal to H times F0. And so my work function phi is going to be equal to, now I want it in electron volts, not in joules, so I'm going to write H, which is 6.62 10 to the negative 34, multiplied by F, which is 3.2 10 to the 15, divided by 6.62. And I need to divide that by 1.6 10 to the negative 19. That's because 1 electron volt is 1.6 10 to the negative 19 joules, and so that converts the whole thing into electron volts. Okay, so this is going to simplify. 6.62 goes away, and I'm going to get 3.2 over 1.6, that's going to be 2, and then minus 34 plus 15 is minus 19, and so this is just going to be 2 at the end of the day. 2 electron volts for the work function. That is the amount of energy I have to pay for an electron to come unbound. Okay. Okay, so now we do the following. We set the frequency of the lamp to 10 times this frequency. Okay, 10 times F0. What is the maximum kinetic energy with which the electrons are ejected from the plate? From the metal plate, not the top plate, from this guy. Okay, well, the energy of a photon is proportional to frequency, right? So what we have here in the first question, this is the minimum energy that a photon must have for the electron to be ejected with no speed whatsoever. Now, if you multiply the frequency by 10, you provide the photon with 10 times more energy. So not only can it pay the 2 electron volt work function, it can also transfer the excess energy to the electron in the form of kinetic energy. So now we're going to say, well, still using the formula from the photoelectric effect, K max is HF minus phi. That's 10 HF0 minus phi. And if I want everything in electron volt, I'll leave phi in electron volt and I'll just convert this. So this is going to be 10 times 6.62, 10 to the negative 34, multiplied by 3.2, 10 to the 15, divided by 6.62, divided by 1.6, 10 to the negative 19, minus 2. Okay, if I were a little bit smarter, which wasn't today, I'd say 10 is the only difference between this, and I already know that that is 2 electron volts, so this is really 20 minus 2 electron volts, which is 18. So anyway, well, when you don't have a brain, you gotta do a little bit of extra work. So 20 minus 2, that's going to be 18 electron volts, but I could have saved myself the trouble. Anyway, that is the kinetic energy with which the fastest electrons will be ejected from the metal. Okay. And then with what speed V upper do the fastest electrons hit the metal plate that has an electric potential V minus? Express V upper in terms of HF0, phi, E, and V minus, along with ME, the mass of the electron. Okay, so earlier I said, I should explain this just for clarity. Earlier I said, okay, well, when V is equal to Vs, the stopping potential, then the electrons turn around right before they hit the plate at the top. Okay, now that's not quite what we have here. What we have here is a bit of a different scenario. We have a scenario where we're told that this is V minus, and therefore the electrons are not necessarily going to turn around right before they hit the plate. In fact, they're going to strike the plate with, we are told, a speed V upper. Okay, and the question is, what is that speed? Now, it should be less than the speed with which they leave the metal plate because, well, the top plate is negative, so it is going to repel them. But it's not the situation where we're trying to find the stopping potential. Instead, we're saying, well, there's a certain amount of potential V minus. Can you find V upper? And it's the same kind of solving, though. So what we're going to do is we're going to write conservation of energy between here and here, because the only force acting on the electron is the electric force from the top plate. And so we're going to say that by conservation of energy, since the electric force is conservative, we have the following. The initial kinetic energy, which is K max when the electron is ejected right here, is going to be added to potential energy. Now, potential energy is electric potential energy, which is QV. Q is the charge of the electron minus E times Vm, which by the way is 0, so that goes away, is equal to 1/2 Me V upper squared plus potential energy minus E V minus. And we're just solving for V upper. Keeping in mind, of course, that K max is equal to HF minus phi. Right? So, in fact, it's the same frequency as before, so it's 10 HF0 minus phi plus E V minus is equal to 1/2 Me V upper squared. And then I'm going to solve for V upper. I am going to multiply by 2, divide by Me, and then take the square root, keep the positive root. All right, so 2 times all of this divided by the mass of the electron going to square root this, keep the positive root because I'm looking for speed, and that is going to be V upper. Okay, so pretty classic, right? We have two equations when it comes to the photoelectric effect. We have this equation right here, which gives us the kinetic energy of the fastest photoelectrons. And then we typically have conservation of energy between the metal and the top plate. And if we were looking for the stopping potential, we would say this is Vs and this is 0, and we could solve for Vs. But you don't always have to be solving for the top stopping potential. You could just be trying to find, let's say, V upper in this case. Okay. So that's the photoelectric effect, which it's not so bad. It's quite straightforward as a problem usually. All right. So now we're going to talk about the particle in a box problem, basically. We're going to do this first problem, which is pretty conceptual. There's formulas, but we're not doing calculus. We're not doing heavy-duty math. And we're just going to try to go over conceptually what's going on to the extent that that's possible and that it helps us understand what's really happening in this problem. So we have a particle of mass m that is trapped in a one-dimensional infinite potential well of width L that is in an excited state. Okay. And as you try to detect it, you find that for the left third of the interval, so that is between 0 and L over 3, the most likely place you find the particle is, well, it shouldn't say at L over 8. I amended that. It should say in a small neighborhood or a small interval centered around L over 8. But that's where you're the most likely to find the particle. Okay. So sketch the wave function for this state and find the wavelength, momentum, and kinetic energy of the particle in this state. All right. So let's do this first. Let's go ahead and, how am I going to do this? I need to, okay. Yeah, because I want to divide it in thirds, so maybe I do this. Okay, so this is going to be L, this is going to be 0. And now what's this wave function thing? The wave function is, basically it is, you can think of it as it is the best quantum description of the particle state. Let's put it that way. Which means that if for a given particle you were to give me the wave function, that would be the best piece of information you could give me. Because I could find everything I need to know about this particle based on the wave function. And the wave function is this weird function that comes from somewhere, which is called Schrödinger's equation. And Schrödinger's equation, talk about that in the next problem, or we'll talk about the simplified version of the Schrödinger equation that we deal with anyway. Schrödinger's equation is basically a partial differential equation, and if you know how to solve it, you can get the wave function for your particle. And we don't typically solve it, but we do, in the case of problems that are a bit more math heavy, either give you the wave function and tell you to prove that it's a function, it's the solution, or we tell you what it is and then you go play around with it. But the point is, a wave function in quantum physics is the most accurate description of the quantum state of your particle. And the wave function has a property, which is that if I take the wave function and I square it, then I'm going to get psi squared, which is a probability density, meaning it is going to be a function, psi squared, that when I graph it, the area under the curve of that the area under the curve of that function is going to represent the probability of finding the particle in that region. So all that to say this: if you are told that the most likely place that you can find the particle in the left third of the box is at L over 8, then, well, let's figure out where L over 8 is, and we'll draw a max but for psi squared, not for psi. So this is going to be L over 2, and then L over 4 is here. This is not a good scale. I need to rethink my scale here. This is no bueno. Hold on. So I need to, okay, I need to make it easy to split into fourths. So I'm going to do this. So this is a fourth, half, 3/4 L. Okay, this is going to be L over 8. And here is going to be psi squared. And what we're saying is that since the area under the curve of psi squared is the probability of finding the particle in that region, then we can conclude that we have to have a max at L over 8 for psi squared. And it turns out that when it comes to these functions, all the max and mins are evenly spaced. So let's just draw what we would draw for here for L over 8. We would draw something like this. Probably. That's pretty terrible, but let's see if we can do better than that. Okay, so that's going to be at L over 8. We have a maximum here. And then, of course, this repeats. So the pattern is going to repeat, and all these max and mins are evenly spaced. All right. All right, so we're not going to get a scholarship to any art institute here, but that's the point, is to just show where the max is. And because of that, then we know, this is L over 2, this is L over 4, this is 3L over 4. Well, what's this, this, and this? This is going to be 3L over 8. This is going to be 5L over 8 and 7L over 8. Right, so right here, right here, right here, and right here. So I use the information that I'm given about the probability of finding the particle in some region to actually graph psi squared to begin with, because psi squared is associated with the probability of finding the particle. But it's not what the question asks me to sketch. This question asks me to sketch the wave function, not the wave function squared. And so I can certainly graph the wave function, but that is going to look something like this. So this is going to be from 0 to L, L over 4, L over 2, 3L over 4. And the wave function is going to look something like this. All right. And I know that if this is psi and this is L over 2, then the wavelength lambda sub n here is equal to L over 2. And the formula for the wavelengths is 2L over n. So it means 2L over n is equal to L over 2. And so I can solve for n. I'm going to find that n is equal to 4. And n is equal to 4 is going to tell me the state that I'm in. So I'm in the fourth state, in other words, the third excited state, because n equals 1 is the ground state. And now I can find the wavelength, the momentum, and the kinetic energy of the particle. So the wavelength I already got because I just read it off of here, right? This is one wavelength, so that's L over 2. So we can say that lambda, or let's call it lambda 4, is L over 2. Then we have the momentum. Okay, momentum. Well, I'm going to use the de Broglie wavelength formula. Lambda is h over p, meaning that p is h over lambda.
So h over lambda 4 is P4, and that's going to be 2h over L. And then to get the kinetic energy, call it K4, that's going to be, I'll use the formula that gives kinetic energy in terms of momentum directly, going to be P4 squared over 2m, and that's going to be 4h squared over L squared divided by 2m, so that's going to be 2h squared over m L squared. That's going to be the kinetic energy. Okay, so that is how I get not only psi, but from psi, now that I know n, I can figure out a lot of stuff. I can figure out wavelength, P4 and K4, right? But important to realize that when it comes to the probability of finding the particle, you're talking about psi squared. So you should be comfortable drawing psi and psi squared for n equals 1, 2, 3, 4, 5. I mean, after that, you can just generalize. You just add basically an antinode, right? But you have to know how to draw psi and psi squared, at least for the first 4 states, because that's very common. Okay, so then, next question, it's a really good question, says that for the particle in the excited state, which is n equals 4 here, it can emit a photon with E photon equal to 3/4 of the particle's initial energy. True or false? If so, what is the final state? If not, sure, why not? So, can we have a photon that's emitted that's 3/4 of the initial particle's energy? So, let's do this. First of all, let's recall that the energy levels E sub n, when it comes to the particle in the box, are equal to n squared times E1. And so that means that if I were to draw the energy levels here, at least the first 4, I would have E1 would be my ground state, that's my lowest level. Then, not too far up from there, I would have E2, which would be 4 times E1. Then E3 is going to be 9 times E1. And this is not to scale by any means, E4 is going to be 16 times E1. And our particle is here in the n equals 4 state. Okay. With that in mind, we can then try to figure out what photons it can emit in terms of energy, right? So you're going to get a photon. This works exactly like the hydrogen atom, by the way. You will get a photon emitted, spontaneous emission, if your particle, electron or otherwise, drops from one level down to another one. In other words, drops to a lower energy state. And then it will emit a photon with an energy exactly equal to the difference in energy between the levels. So let's start by drawing the different transitions that we can have. Okay. All in all, if you start out at n is equal to 4 and you go all the way down to E1, you can do it a few different ways. You can go straight down to E1, okay? No messing around, just straight down to E1. But you're not told that you go from 4 to 1. You're just told that you're in an excited state, and obviously if you want to emit a photon, you have to drop to a lower energy state, but it doesn't say it has to be E1. So you have to entertain the possibility that you would drop maybe to E2 instead, or even E3. Right, so that's 3 options right there. However, that's only part of the story, because if you do drop, let's say, to E3, well, then from there you could then directly go to E1, or you could go to E2. Right? That's a different transition, so different photon with a different energy that would be emitted. And then, of course, if you are going to end up on E2 anyway, you could then go from E2 to E1. So we have 6 possible transitions. The question is any one of these transitions such that the emitted photon has an energy that is 3/4 of the particle's initial energy? Okay, so that would mean that we want E photon to have an energy that is 3/4 of the particle's initial energy, which is E4. All right, so that's 3/4 times 16 E1. That's going to be 12 E1. So the question then is, are there 2 levels that have a difference in energy between them in absolute value that is 12 E1 exactly? Because if that's the case, then I will emit a photon with exactly this amount of energy. Okay, so if 2 levels have an energy difference of 12 E1 in magnitude, or in absolute value, same thing, then such a photon can be emitted. Okay, well, you probably already figured it out. It's 16 to 4 is going to work, right? But if you check, okay, 16 to 9, no, that's 7 E1. 16 to 1, that's 15 E1, and so on and so forth. So in this case, yes, the transition four to 2 will emit a photon with energy absolute value of E2 minus E4 is equal to 12 E1, which is 3/4 of E4. So yes, it is possible to emit a photon with that energy. All right. And so then, last question asks, for the particle in the original excited state, so n equals 4, what is the largest energy photon it can emit? And after doing so, will it be more, less, or the same likely? Okay, does the likelihood stay the same, increase, or decrease of finding the particle at L is equal to x is equal to L over 4? Okay, let's go have a look. If we're trying to emit a photon, obviously we have to transition to a lower energy level. But if we want the photon that is emitted to have the largest possible energy, then we have to choose the transition between the 2 energy levels that are the furthest apart. And so that is going to be the transition from 4 to 1. Okay, so that is the largest energy difference. That will emit the photon with the biggest energy, which will be E photon is 15 E1. Okay, so the transition 4 to 1 will emit the highest energy photon because the energy difference between these levels is the greatest. And so we will conclude that the energy of such a photon is going to be, of course, it's the absolute value of the difference between the energies. So E1 minus E4 in absolute value, and that's going to be 15 E1. All right, now that tells you that the transition has to be from 4 to 1. And now the question is, well, am I more likely to find the particle around L over 4 in the initial state, n equals 4, or in the final state, n equals 1? Okay, good question. Let's go back to this thing here. Let's grab this because this is our starting point anyway. So I'm going to make a copy of this and I'll bring it down here. And then let's draw psi 1 squared. So this is psi 4 squared. I want to draw psi 1 squared. Okay. Now psi 1 squared is going to look something like this. Should be perfectly symmetric, but close enough. You get the idea. The max here is at L over 2. And so the highest likelihood of finding the particle in this state is around L over 2. Let's compare L over 4. Well, here, it's pretty easy. L over 4 here, even if the probability isn't 0, it's really close to 0, right? Now, in theory, you'd have to consider some tiny interval, right, around L over 4. So that's a tiny, tiny amount of area, but it's not 0. Versus, okay, well, if I look at the same interval around L over 4 here, from here to here, obviously here I have more area. And so the probability, what just happened here? There we go. Okay. The probability of finding the particle around L over 4 is higher in the n equals 1 state. Okay. Now you might say, oh, well, how do you know? Because how do you know what this area is total versus this area here total? Now, well, they're both equal to 1, right? The total area under the curve is the probability of finding the particle somewhere in the box, which is 100% because the particle has to be in the box. So this is actually 25% chance of finding it here, 25% here, and so on and so forth, versus, well, all of this is 100%. But the idea, of course, here is that it's pretty unambiguous because if you compare the area around L over 4 here versus here, obviously the area is greater when you're in the first state, or you're in the state n is equal to 1, I should say. Okay, now I highlighted around here because this is semantics, but sometimes this question pops up. The question will go something like this. It'll say, oh, well, what is the probability of finding the particle at 3L over 8? Let's say. Okay, the probability of finding the particle at exactly 3L over 8 or any other value, doesn't matter if it's 3L over 8 or somewhere here or somewhere here. If you say that you want the probability of finding the particle exactly at 3L over 8, the answer is 0. Because exactly at 3L over 8 does not define an area under the curve. Okay. Now, if you say, well, is the probability max or min of finding the particle around 3L over 8, then okay, around 3L over 8 means in a tiny interval centered on 3L over 8, and then I'll say, well, that's the max probability, right? It's the same as the max probability around these values as well, But overall, yes, it's a max probability, not a min. So that's just kind of playing with words, but be careful with words. In order to define a probability of presence, you need some area. So if the question is exactly at L over 2, what is the probability of finding the particle? The answer is necessarily 0, because exactly at L over 2 does not define an area under the curve. Okay, so I like this problem. It's a good recap of the important equations associated with the particle in the box. If your goal is just to use the formulas and not rederive them in any way or not dive into calculus. Now, speaking of diving into calculus, let's do one of these, because it's one of these things, if we do it, then probably it won't be on the final. But if we don't, guess what? It will be. So what I'm going to do is I want to solve the 3 most important questions you might get when it comes to Schrodinger's equation and the particle in a box. And I mean, I'll throw a couple of other ones in there as well, but the 3 main ones are the important ones. They're finding the constant A, which we use the normalization condition, finding the wavelengths, and finding the energy levels by subbing back into Schrodinger's equation. So this problem is actually a really, really long problem. It's got like 9 questions. I just cut off the top to talk about the setup, and then I added my questions here. So I'll post that all online. You'll get this truncated version, but you shouldn't need more than that to think about it. And we're given any antiderivative we might need, and we're told a whole bunch of stuff. We're told that the particle is in a box basically that's centered, or that's extends between 0 and L, for which potential energy is 0, but outside of the walls of the box, potential energy is infinity. So, like, okay, like what does that exactly mean? So let's start with that. The drawing that you'll probably find is something like this. So this is going to be 0, this is going to be L, and that's our box. And if we want the particle to be confined to this box, at least in theory, we have to have regions outside of this box where the potential energy is mathematically infinity. Now, is that realistic in the real world? Probably not. But in the real world, all we would need this to be, rather than infinity, is an amount of energy so large that the particle couldn't acquire it on its own, right? It couldn't acquire it with like heat or sunlight or whatever you want to think of that might provide energy. The amount is too big for it to go from being in the box to jumping over the wall, okay? So mathematically, though, we are going to create walls that are infinitely high by letting the potential energy in these regions, U1 and U3, go to infinity. Okay, now this is going to be region 1, this is region 2, this is the box, and region 3. And then we're saying, well, okay, and there's going to be 3 wave functions. Each region is going to have its own wave function, which kind of makes sense, because if the wave function gives me the quantum description of this particle, and also if I square the wave function, I'm going to get probability of finding the particle in that region, probably each region should have its own psi. So this simple drawing is really what this thing is saying, but you've probably noticed that a lot of physicists don't like drawing, so they just type this up and they're like, everybody gets it. So that's all this is saying, okay? Now what we want to do is find psi for each region. We're going to start with 1 and 3, because we can find that on our own. And then for region 2, somebody has to give us the function. Okay, so we're not going to try to do anything on our own, as in solve Schrodinger. We don't know how, but someone will give us a function. In fact, you know what? Let me make this a smidge more interesting. I'm going to do this, because it might be given to you like this. plus b sine kx.
Okay, and so then Schrödinger's equation is going to be given to you one way or the other, either straight up in the problem or on your formula sheet, but you're not expected to know Schrödinger's equation off the top of your head. So minus h bar over 2m d2 psi dx squared plus u psi is equal to e psi. Okay. Now we're not going to try to figure out what this thing is saying because, as is the case in most of quantum, the answer is who knows. But what we do want to know is that psi denotes the wave function, and the wave function is going to satisfy this equation. U is the potential energy, and E is going to give me my energy levels, and we'll see that later. And so the first question is, can you find psi in regions 1 and 3? Okay, well, let's see. In region 1, I have the following. I have Schrödinger's equation, and in region 1, the wave function is psi 1. So psi 1 is going to be the solution, or is going to satisfy, if you will, Schrödinger's equation. So I can write this relationship. What I'm going to do then is I'm going to divide, actually I should do this, I should say it's going to be U1 as well because potential energy is specific to each region. Now I'm going to divide every term by the potential energy. So if I do that, I'm going to get minus h bar squared 2m u1 d2 psi 1 over dx squared plus psi 1 is equal to e over u 1 times psi 1. And, well, hey, if u1 is infinitely large, this is pretty much 0, and this is pretty much 0. And so my conclusion is that psi 1 is going to have to be 0. There's no choice. Now this actually makes sense because if you remember, let's say I had psi 1 and it's non-zero. Then I square it, I get psi 1 squared. Like, oh, I get the function that when I graph it, the area under the curve tells me the probability of finding the particle. Well, the probability of finding the particle outside the box is flat out 0. That's why the walls of the box are infinitely high. It's because I don't want it outside of the box. I want it in between 0 and L. So it would stand to reason that then psi 1 squared would have to be 0. The only way that that can be is if psi 1 is equal to 0. So in region 1, psi 1 will be 0. In region 3, you can copy-paste the exact same reasoning, just change u1 to u3 and psi 1 to psi 3. In region 3, similarly, because I already did the work up there, psi 3 is 0. Okay, so outside of the box, there is no chance that I will find my particle. Good, because that's kind of the point. I want it trapped within this box. Now sometimes we don't say box, we say potential well. It means the same thing, right? It's a well of potential energy that's infinitely deep, and the particle is trapped in there. Okay, then let's do this question here. Using psi 2 given in this form, now this would be given. Although I say that we're going to find the exact form of psi 2 in the end, I would still memorize that as an insurance policy before I go into the exam. Just in case, for whatever creative reason, you're supposed to know it and apply it to the problem. But usually we'll give it to you, because it's like, there's
no point. There's nothing you can lean on to solve to get psi 2 if you don't know what it looks like. Okay, so let's, using psi 2 in this form, solve for A, solve for lambda, solve for E. In each case, it is always the same method. It might be tweaked here and there in terms of what you write for the math, depending on if the problem gets tweaked a little bit. If you have instead of a box, you have a ring or whatever. Like, sometimes it gets creative, but the process is the same. So the way that I solve for A is by using the normalization condition. The way I solve for lambda is by using the boundary conditions, and the way I solve for E is by using Schrodinger's equation. So let's do this in a logical order. And that's kind of my bad. I should have phrased my question a little bit better. I should have said lambda n, then en, and then kept a for the end, for the last one. That makes a little bit more sense to do it in that order. Okay. So for lambda, we're going to use the boundary conditions. For E, we're going to use Schrodinger. For A, we're going to use the normalization condition. Okay. So my boundary conditions are well, psi 2, whatever it is, doesn't really matter what psi 2 looks like, but let's say it looks something like this. Okay, at least in the state n is equal to 1. Psi 2 within the box can be whatever it wants to be, but it has to be continuous at the edges, and so since psi 1 is 0 and psi 3 is 0, then I have no choice. I must have psi 2 at x equals 0 is equal to 0, and psi 2 at x equals L is also equal to 0. All right. Well, let's start with the first one. Psi 2 at x equals 0 is equal to 0 implies that A cosine of 0, because x is 0, plus B sine of 0, because x is 0, is equal to 0, obviously. My bad, hold on. Doesn't really matter, but since I call it A, let's put the constants in different order. Okay, A and B are constants. The point is, by using the boundary condition, you're going to find that one of the constants is 0. It should be the constant associated with sine. And, no, the constant associated with cosine, I'm sorry. And then the other one that's going to survive, therefore, is the one associated with sine. So sine of 0 is 0. In other words, b cosine 0 being 1, is 0. So then b has to be equal to 0. Okay, so b is 0. That takes that out of the equation. So I can get rid of all of this. It's not going to matter. Okay. So then, if I write psi 2 of x equals L is equal to 0, well, remember that at this point, psi 2 is just equal to this. Right? So this means that A sine KL has to be equal to 0. And as a reminder, K is 2 pi over lambda. So this means that A sine KL, which is 2 pi over lambda, times L, has to be 0. Now, in theory, there are two options. A could be 0, but if A is 0, I mean, then this goes away and I have no wave function, so that does not make any sense. So A itself here cannot be 0, meaning I need sine 2 pi L over lambda to be 0, which means that I need 2 pi L over lambda to be equal to n times pi, where n is equal to 0, 1, 2, and so on and so forth. Okay. Now in theory, 0 would work because, you know, if I had 0, sine of 0 is 0, but the thing is, this is never going to be 0, right? It's 2 pi L is the length, lambda is a wavelength, so really it starts at n is equal to 1, and then 2, 3, and so on and so forth. Okay. Now that means that the wavelengths that are acceptable, let's call them lambda sub n, are going to be 2L over n. By the way, that's what we saw in the previous problem. So for n is equal to 1, 2, 3, etc. All right. So that's lambda n. Those are the wavelengths that are associated with the different energy levels, or the different states. Okay? So that's the first part, which was solving for lambda, and you do that using the boundary conditions. In the process, the boundary conditions are going to knock out this term that is useless in psi 2, leaving psi 2 to be something of this form. Right? And again, maybe we just give it to you like this initially, but maybe we give it to you like this and we have you solve and find that b is equal to 0. Okay, so then now let's find the energy levels. Okay, so we have psi 2 of x is equal to a sine kx. And we're in region 2 within the box where we know that the potential energy is 0. So how do we find the energy levels? We find the energy levels by subbing psi 2, in this case, back into Schrödinger's equation. So we're going to say, well, we have Schrödinger's equation. That's minus h bar squared over 2m d2 psi 2 over dx squared plus u2 psi 2 is equal to e psi 2. And because u is equal to 0 in the box, this term drops out. So I'm just left with this is equal to this. And the fact that psi 2 is a solution to Schrödinger's equation means that psi 2 satisfies the equation. In other words, if I were to find the second derivative and plug it into here, I could set these two equal to each other and the equation would be true. So that's what we're going to do. We're going to find the second derivative of psi 2. Okay? Now recall real quick the chain rule before we do that. Sine of u prime is u prime cosine u, and cosine of u prime is minus u prime sine of u. All right. So let's find the first derivative and then we'll get the second derivative. So psi 2 prime of x is going to be a times k times cosine kx. And then if I take the derivative again, psi 2 double prime, which is this thing, is going to be now minus k squared a sine kx. Now something to note is that this is this, and so this is minus k squared psi 2. Pretty useful, because now if I plug that back into here, I'm going to get minus h bar squared over 2m times, well, what's the second derivative? Apparently it's minus k squared psi 2 plus 0, because this goes away, is equal to E times psi 2. Okay, well, psi 2 might be many things depending on n, but one thing it is not is 0. So if it's not 0, I can divide both sides by psi 2 and it goes away. And that gives me that the energy levels E, which we're going to call E sub n, and you'll see why, are k squared h bar squared over 2m. But if you recall what k is 2 pi over lambda, right? So k is 2 pi over lambda. And so if it's 2 pi over lambda and lambda is 2L over n, then k is equal to hold on. Okay, it's 2 pi over lambda, which is 2 pi divided by 2L over n, so duh is n pi over L is k. So this is going to be n squared pi squared h bar squared divided by 2m L squared. And now it depends how you want to write the energy levels. If you want to write them in this form, which is fine, or if you prefer to write them in terms of h, just remember that h bar is h over 2 pi, so you could change this and you could write it in terms of h. So, or using h bar is h over 2 pi, E sub n is going to be equal to, well, if I sub in h over 2 pi for h bar, I'm going to get n squared h squared over 4 times 2 is 8m L squared. And n is going to be 1, 2, 3, etc. All right. So classic question, and pretty classic to have you sub psi back into Schrodinger's equation. So you should be comfortable taking the derivative twice and plugging it back in, typically to get the energy levels. Okay. So then the third and last question is finding this constant a. Right? So we've been saying that psi 2 is a sine kx, which wasn't an issue here because psi 2 simplifies out anyway. But can we find what this constant a is? Okay. Now this is called the normalization condition. The normalization condition says that the probability of finding the particle somewhere in space is 100%. So if I were to integrate over all of space psi squared dx, I should get 1, which corresponds to 100%. The thing is, because my particle is not just anywhere in space, it is in fact stuck on this interval between 0 and L, it really means that what I have to do is integrate from 0 to L psi squared dx, because everywhere outside of that psi is 0, and then I'm going to get 1. And of course that would be psi 2 in this case. So in our particular case, the normalization condition becomes this, and there is only one constant a that makes this true. Okay? So let's, just as a reminder, so that we don't scroll up and down, recall that we have that the integral of sine squared kx dx is equal to 1/2 x minus 1 over 2k sine 2kx. Okay, and by the way, psi 2 of x is equal to a sine kx. Okay, so we are saying that the integral from 0 to L of psi 2 squared, which is a squared sine squared of kx dx, has to equal 1. Well, that means that a squared is a constant, so integrals don't care about constants. I can move it outside. A squared multiplied by this antiderivative, pretty much, because I'm going to be left with the integral of sine squared kx dx. So a squared really over 2 times x minus 1 over 2k sine 2kx between 0 and L has to be 1. Okay. Well, that's a squared over 2. Plug in the upper bound first, so L minus 1 over 2k sine of, now if you recall, we said earlier k is n pi over L, right? So this is going to be 2n pi, x is L, divided by L. And then minus, when I plug in 0, this becomes 0, and sine of 0 is 0. So the lower bound just cancels everything. Okay. And then sine of 2n pi is actually always going to be equal to 0. Because sine of 2 pi, when n is 1, is 0. Sine of 4 pi is 0, so on and so forth. So all of this goes away, and we're left with a squared times L over 2 has to be 1. The only value of a that makes this all work is therefore going to be square root of 2 over L. All right. And so we conclude that psi 2 of x is square root of 2 over L times sine of n pi x over L. And it ought to be the case that either you're going to derive this, that's the point of the problem, or if you need it for whatever reason, we'll pretty much give it to you. However, as an insurance policy, I would memorize that. Okay, like if I memorize it and somebody decides to give it to me, they're like, okay, fine, easy, high quality problem. But I wouldn't want to stumble on a problem where, well, it's not given and I needed it, and somehow for whatever reason I was expected to know it. Okay, so that's just thinking in practical and terms and in actuarial terms, if you want to think of it that way. So anyway, those are the most classic questions that you'll get with particle in a box. I mean, this one, why not? It's kind of interesting just to understand why psi is 0 outside of the box. But these, for sure, are technical questions that you'll get. Very, very likely. Okay. So boundary conditions will give you lambda, and will also tell you that this term goes away. And then energy levels are derived by subbing the wave function back into Schrodinger, and then you get energy levels. And then the constant A that is the right constant to describe the particle in the box is going to satisfy the normalization condition. And the normalization condition says that if you integrate over the entire box of psi squared, then you have to get 1, which is a 100% chance of finding the particle somewhere in the box. Doesn't tell you where, it just tells you it's somewhere in the box. And then speaking of telling you where, let's do the last question, which is, what is the probability of finding the particle in the region 0 L over 4? Okay, so in other words, what is the probability that the particle will be located at some x between 0 and L over 4? Okay, now by definition, kind of already know what that is, right? We said, well, that's going to be the area under the curve of the probability density function, which is psi squared. Okay, and we're going to assume n is equal to 1 here. So you could do it for any state, but we're going to assume that we're doing it for the ground state. Okay, so you're telling me that I want the probability that the particle be in the left quarter of the box. That probability is going to have to be given by the area under the curve of psi 1 squared. Well, psi squared for n equals 1. That's how I should really say it. And so this is going to be the integral from 0 to L over 4 of psi 2 squared dx. Right. And so that's going to be the integral from 0 to L over 4 of, well, 2 over L, because I squared psi 2, sine of pi x over L dx. Okay, just to be clear, here the n, where did it go? Well, we're assuming n is equal to 1. So that's why I have that. Okay. And so this is going to be 2 over L times the antiderivative, 1/2 of the following. So it's x minus L over 2k sine of 2kx between 0 and L over 4. Just recall that k here is pi over L. Okay, and so this actually should be 1 right here. There we go. Okay, so then this is going to be 2 goes away, 1 over L. It's going to be x minus L over 2 pi sine of 2 pi x over L between 0 and L over 4. All right, so this is 1 over L. Now we'll plug in the upper bound. X is equal to L over 4 minus L over 2 pi sine of 2 pi L over 4. Minus, when x is equal to 0, this is 0, sine of 0 is 0, so the lower bound cancels everything. And I'm going to get, now let's see, I'm going to get 1 over L times L over 4 minus L over 2 pi sine of, L goes away, pi over 2. Okay, now sine of pi over 2 is actually 1. And so if I distribute the 1 over L, I'm going to get 1/4 minus 1 over 2 pi. And that is approximately equal to 0.091. In other words, 9.1% chance of finding the particle in the left quarter of the box.